70,000 cubic meters of water flow past here every minute at almost 60 kilometers per hour. That's enough water to fill about 100,000 Olympic swimming pools every day. Standing here, you can actually feel the power of the water. Harnessing that power is what hydroelectric stations have been designed to do for over 100 years in Ontario. In essence, they are factories that convert the energy of falling water into the flow of electrons, or what is commonly called electricity, the electricity that powers the province. Most hydroelectric stations use either water diverted around the natural drop of a river, such as a waterfall or rapids, or a dam is built across a river to raise the water level and provide the drop needed to create a driving force. Water at the higher level is collected in the forebay. It flows through the plant intake into a pipe called a penstock, which carries it down to a turbine water wheel at the lower water level. The water pressure increases as it flows down the penstock. It is this pressure and flow that drives the turbine that is connected to the generator. Inside the generator is the rotor that is spun by the turbine. Large electromagnets are attached to the rotor located within coils of copper wire called the stator. As the generator rotor spins the magnets, a flow of electrons is created in the coils of the stator. This produces electricity that can be stepped up in voltage through the station transformers and sent across transmission lines. The falling water, having served its purpose, exits the generating station to the tail race, where it rejoins the main stream of the river to continue the cycle of creating clean, renewable energy for Ontario.
Geothermal energy gives us a steady supply of electrical power with minimal environmental impact. Here is the basic process. Water in underground reservoirs is heated to high temperatures by magma. Production wells drilled up to 10,000 feet below the Earth's surface tap into this hot fluid. Under its own pressure, the fluid flows through these wells toward the surface. As it travels, the pressure lessens, causing a small amount to become steam. Together, the hot fluid and steam move through a surface pipeline to a wellhead separator, where the pressure is reduced. Here, most of the fluid vaporizes and flashes into high-pressure steam. Any fluid not flashed into steam moves to a standard pressure crystallizer to produce standard pressure steam. Remaining fluid is then flashed at a lower pressure to create low-pressure steam. All steam created in the plant is sent to a turbine on site. The force of the steam spins the turbine's blades, which turns a shaft connected to an electrical generator. An electrical charge is created and directed to a transformer, where the voltage is increased and sent down power lines. Any fluids not flashed into steam return to the underground reservoir, where, in time, they will be reheated and reused. Geothermal energy, a simple, clean, and renewable energy.
Everybody's talking about carbon these days. Carbon emissions, carbon footprints, and even more about global warming. As we burn more and more fossil fuels like coal and oil, we damage our world. We need a green alternative. We need to burn green. What kind of fire burns green? It's a fire burning a fuel that is clean and doesn't add to global warming, renewable and renews quickly, and of course inexpensive compared to coal and oil. These are biomass fuels. Biomass fuels are made from a variety of materials. Plants such as willow or rapeseed, poplar or hemp, even biodegradable wastes. And they replace fuels like coal or oil for central heating in your home. Biomass fuels are carbon neutral. They are part of the carbon cycle. Carbon from the atmosphere is absorbed into plants during photosynthesis, and when the plant decays or is burnt, that carbon goes back into the atmosphere. But because it's a cycle, the next crop of plants absorb that carbon over again. So there is a balance between the amount of carbon that the biomass fuels release into the atmosphere and the amount that they extract from it. This is why biomass fuels do not contribute to global warming. So, biomass fuels are clean. Growing them takes as much carbon out of the air as burning puts into it. Biomass fuels are renewable. As you convert this year's crop to fuel, you are growing another one for next year's fuel. Renewing takes just as long as it takes to grow, and that can be as little as months in some cases. Biomass fuels are inexpensive compared to coal or oil. Typically, they cost about 1/3 less than a fossil fuel doing the same job. This means you spend 1/3 less every year on heating your home. And over 10, 15 or 20 years, that adds up to a considerable saving. There are different types of biomass fuels. Pellets, wood chips and wood logs are among the most common, but there are other forms too. They are used in specially designed stoves and boilers. These are highly efficient. Virtually no energy is wasted, unlike a back boiler where half of the energy goes up the chimney. They are clean to use. Biomass fuels burn very efficiently. A single bag of pellets will power a boiler or stove for 2 or 3 days, and they produce very little ash, especially when compared to coal. And a full year's supply of pellets would take up no more than 1/3 of an ordinary domestic garage.
Oceans cover 3/4 of the Earth's surface, and harnessing their power could help navigate our way to energy independence. 4 miles off the New Jersey coast, this buoy is an actual floating power plant.
Heading down underneath.
Divers connect the buoy to an underwater cable. As it bounces up and down with the waves, its energy generates electricity.
Our system is unique in the sense that we are able to tune it to the actual wave, and during the beginning of the wave the computer adjusts the system to extract the maximum energy.
This buoy generates enough power for 40 homes. The next generation will produce 4 times as much. Wave farms of 10 buoys are planned for Spain, Scotland and Oregon.
If you double the wave height, you get 4 times the amount.
Work. The tail fin points the propeller into the wind, causing it to spin. The propeller rotates the shaft, and the shaft turns the generator. This generates electricity. The converter makes the AC into DC power, and the battery stores the power for a stable output. And that is how wind turbines work.
Electricity from sunlight, and here's a silicon solar cell. The sun sends about 1,000 watts per square meter to the earth every time it shines, right? We can use silicon solar cells to make electricity directly from the sun energy. The sunlight hits the silicon, the blue surface here, and the impact creates a free electron in the silicon, and that electron is collected by these aluminum traces here and then connected together with the rest of the silicon cells and then used in your house as electricity. Now, this is a very nice idea, but today it's still quite expensive to do this. The electricity from silicon solar cells is almost 3 times as expensive as what you pay for in your utility. So the challenge for us is to do research and come up with technologies that significantly reduce the cost of making electricity from sunlight. And so here is one example, right? We've been doing research on different types of silicon and different ways of processing silicon. And this solar shed that looks very similar to the one I've shown you actually produces almost the same amount of electricity as the big one, being about half the size. So this one is twice as efficient as the big one, and so you see it uses half as much material, so we roughly cut the cost in half. It's a very interesting idea. We're looking at some advanced research in nanotechnology that will cut the size and the cost of these cells further by a factor of 2 in the future. Now, the next question is, these solar cells are a little bit rigid. They come in these boxes that you put on the roof, and they don't integrate very well in the house. Our goal is really to come up with technology that seamlessly integrates with the house and with the building. And so here's an example. Imagine if you could make these cells a little flexible. And here's a little example of that. Some electronics on a flexible substrate. If you had a cell like this, you could really make a shingle out of it. You could make it very simple. You could make a facade material. And so we can come up with techniques that really seamlessly integrate all this power generation from solar with the house that you're building. All right? So overall, we believe that the solar technology is really here. In the next 5 to 10 years, we foresee the future in which 10, 15, even 20% of electricity in the country will be generated from solar energy directly in a very nice, very clean way. And it will be very nice to look at. It will be seamlessly integrated in the house, and you will help buildings that, in addition to providing shelter, also provide electricity and clean energy for the house. My name is Vlatko Vlatkovic. I'm the manager of the Electronics and Energy Conversion Lab. We work on wind, we work on solar, we work on renewable energy. I think the technology that we work on will contribute significantly to the environment, to well-being of the country, as well as